14 of Complexity Explorer's MESA tutorial, Agent-Based Modeling in Python. In this session, we'll begin the first part of our four-part series on trading agents, where the agents will trade sugar and spice in order to hopefully survive and thrive in their environment. Let's get started. First, open up your IDE or Google Colab instance. With your Google Colab instance, you want to make sure that you've set up your sugarmap.txt file either by linking your drive, right, or by uploading via the folders. All right, we have our dependencies, then we have one helper function, two resource classes, right, one class for sugar, one class for spice, our trader agent class, right, which is getting more and more complicated as we continue to build out the functionality, and our model class, right, which manages the interactions of our agent classes. We initiate, and then we have a series of step functions. Right, from our last lesson, right, we're printing out each step, right, and watching the agents that run out of sugar and spice and then are removed from the program. Right, so first we'll remove those print statements because we won't be needing them for this section. So we got one in our step function, and then one in our trader agent, or a couple in our trader agent function. And those are located in our maybe die function at the bottom of the cell. Now that we've removed those, we can start beginning our trader function. All right, so the first thing we have to do, because we've had agents that have been removed from our model because they ran out of sugar or spice, right, is we have to set up our list that allows us to iterate through. Otherwise, we'll end up with an error because our dictionary of agents has changed. Right, so now that we're going to use essentially the same two lines twice to create trader shuffle and then randomize it, we're going to just turn that into a function. So create trader function, and then we'll call this function self dot randomize traders, and it'll take no parameters. And then we can just take these two lines, and I'm going to cut them. And then just turn that into a function inside our model class. Right, so I'll do this above the step function as it's a helper function for step, right, and below all the functions that we use to initiate the model. Okay, so it's fairly simple. Randomize underscore traders, right? Then it takes a parameter self as it's part of our model class. Then we just have trader shuffle equals the list from our schedule of agents. And we want to make sure we add our comments, right? Helper function for our step function. And this just creates a randomized list of our traders, so that way we can avoid challenges of first mover advantage or second mover advantage. And on some models, based off what you're trying to accomplish or show, you might not want to randomize it. But for this model, as we're showing kind of functionality of basic or economic theory, we want to make sure that we randomize it. Okay. After we do that, then we just return our trader shuffle list. All right, so if you remember from previous lessons, the random.shuffle doesn't actually return anything. It just takes that list and changes the order that it's in. Now that we've created our helper function, we can go beneath our for loop, where we iterate through and have our agents move, eat, and possibly die, right? And then shuffle our agent list again, updating it so it does not include any agent that possibly died in that step. All right, now that this is done, we're going to iterate through it again using another for loop. Right, and this is going to be for agent in trader shuffle and then it's just going to call a new function we're about to build called agent trade with neighbors. So this will allow us to continue our somewhat unique activation of random stage activation. So it goes sugar, spice, right? Then our agents move, eat, and possibly die, right? And then after that, our agents trade with each other. So we run that cell to make sure it's stored in memory, right? Then we go back up to our trader agents, right? And as this is a main function, right? So like move, eat, and maybe die, right? Then we add the trade with neighbor functions. Okay, so it's def trade with neighbor self because it's part of our trader agent class. And we add our comments, and this function will proceed in three parts. It's a function for trader agents to decide who to trade with. The three parts that it's going to be is first you got to locate your neighbors and identify all the cells that are in each agent's radius of vision, how many trader agents there are that that trader agent could possibly trade with. So first, like the eat function, first we have to do is identify our neighbors. But in this case, we're actually looking for traders, not avoiding them. And the second thing we do is trade, and that'll actually take 2 sessions. Right? And then the final bit we'll do is collect data off that trade so we can get statistics about how our model's functioning. And then just like the previous, just like the move function, we're going to create we're going to do list comprehension, right, in order to create a list of our neighbor agents. Right, so first for this, we'll need another helper function. So that'll be self get trader, and that'll take one parameter, and that'll be the agent's position. Then we'll be able to use Mace's get neighborhood function. So that's part of our space.py file. So that's stored as self.model.grid, right? Get neighborhood, right? And this takes the same parameters as last time. So first it takes the position, then it takes whether or not you're using your Moore or von Neumann neighborhood. We're using our von Neumann, so that's actually stored as false. Then whether or not to include the center. In this case, we're going to say false because we don't want to include the center because we don't want to trade with ourselves. And then the vision of that agent, which gives a radius of how far they should look. And this time, instead of doing if not occupied by other, we're just going to say if is occupied uh, by other. So we can reuse that function, or in this case, if it has a trader agent, we want them to return that cell. So again, this will use list comprehension in order to create a list of neighbor agents that we could possibly trade with. Okay, so now I got to build our helper function. So I'm going to put this above our main functions, right? And I'm going to put it below our get spice amount, right? So we have this kind of series of functions: get spice, get sugar, get spice amount, get sugar amount. This has that same essentially kind of purpose, but this time we're getting a trader. So I'm going to put it here just to help me keep my code organized. So if I have issues or I'm looking for something, or I want to update something, I know where it's at. Okay, so we create our def get trader, right? Take self because it's part of the trader class, and then one parameter, which is the agent's position. I'm going to add some comments. All right, so again, these are somewhat informal uh, because we're not necessarily specifying specifically the parameter data type it takes, but comments are still crucial so you can come back, months, weeks, days later, and better understand your code as well as help others understand it if they're using your model or reusing it or improving upon it. So this is going to be a helper function used in trade with neighbors. So similar to our previous functions, All right, this is just going to say this cell. We want to retrieve all the contents of the cell, and we use Mace's built-in function from its space.py, which is self.model.grid get cell list contents position. Remember, we stored our multi-grid class, right, in the model in self.grid. So that's why I use self.model.grid. Right, and then for agent, and we iterate through that cell. So we do for agent in this cell. We want to see if any of these agents are in fact a traitor agent. So we can use Python's built-in isInstance function. And if it is in fact a traitor agent, we just return that agent. So fairly straightforward function that just iterates through um, all the cell contents and determines whether or not it's an instance of our traitor. Right? As you can see, we run it. We have a syntax error where I added an extra parentheses. Right here, I got one too many parentheses. Right, so I just delete that, run it again. Okay, and I've removed my syntax error. Okay, so now we've completed our list comprehension to produce a list of neighbor agents that are actually traitors. So now I want to test it. Right, code a little, test a little. And so we'll just print out the list of neighbor agents to see how it's functioning. I'll run that again, no syntax errors. Then make sure the model class is stored and that's updated. And then we will run our instantiation of our class. Yep, I'll get an error where I did uh, local reference error where I called this trade shuffle instead of trader shuffle when I rebuilt those lines of code. It's a fairly easy fix. So trader shuffle, so this is unbound local error because I did trade shuffle instead of trader shuffle. So fix that, and I get another error. Okay, in this case, I get a type error, cannot unpack an interval. You can see here, it's not my code that's erroring out, it's Mesa's space.py when this doing. So that means I've done something wrong when I called this get neighborhood function. Now, whether or not you're in the IDE, uh, your own IDE, or Google Colab, right, we can actually reference that code. Right, but let's go up and see what the error is. So you can see here's the where I call the get neighborhood function, and I called it self, and I forgot the dot pos, right? So I was passing in the agent object, not just the agent's position attribute. All right, so that's fairly easy. We update that. So it's passing in the wrong type of attributes, expecting a tuple of x, y, right? As you can see here, and this is the same with most IDEs, right? I can link this, and this will take me to my locally stored version of space.py, right? And there's where the issue is because it's passing in an agent object, not a tuple that's the position of the agent. Right? And this is no different than what we've shown previously in the lessons where we show our GitHub space.py. Okay, so the code is turtles all the way down, so to speak. The code is just Python for the most part all the way down. As you can see, we're getting a list of trader objects. So it's doing exactly what we hope it's doing. Now it looks a little bit visually messy. Okay, so if we could do something else just to make it cleaner, let's do um, the length of neighbor agents that we're getting back. So just add the length function or length function. All right, store that in memory. As you can see, we get a series of numbers. That's the length of the agents in their neighborhoods. So that wraps up session 14. Develop our trade function. Thanks for joining, and we'll see you next time.